I am going to present the ConvNeXt for 2020 paper. So, in this paper, what they actually trying to do was they try to give better result with the convolution networks than the string transformer. So, and this paper from the Facebook AI research, it's currently called Meta AI. So first thing is, during last week also we talk about the inductive bias in the convolution network. So something like that, and in here convolution networks were perfect for many computer vision tasks because of the it share the similarities between the similarities, and in here we can see in convolution its kernel move like that, and because of that behavior, like in human vision, it's how we perform them, how to perform the natural image processing. Like we look into the image like in this manner, and because of that's why the inductive bias came, like because of that behavior of the convolutional kernels. So when we talk about the transformers, it don't have that kind of inductive bias. It's look at the image, or it's look at these all nodes at once in single time and make the attention to the all the other nodes. We can call the global attention kind of things. So in here mentioned that transformers primarily deal with the relationships between the data. At once all the look at the all the patches and try to find the relationship. So these convolutional methods use this local attention kind of things, and the transformers make the attention to the global, and in the swing transformer they combine both the things, and they use the local attention mechanism to find the relationships. So in this paper, what they did was they tried to improve the convolution network toward the swing transformer model. So they modernized the convolution network with this kind of architectural and the training improvement. What they did was they improved the training methodology, and they increased the accuracy to 78.8. They used the resonate 50 and improved the newest training methodologies, and take that as the baseline, and they improve various architectural improvement, and they finally surpassed the swing transformers accuracies. So in here they did the macro design changes, like changing the internal block design, block count kind of things, and they incorporate the ConvNeXt paper. ConvNeXt means they introduced the group convolution kind of things into the ResNet architecture, and they introduced the inverted bottleneck architecture, and then they tried various kernel sizes, and finally they did micro design. The internal architecture of the blocks are changed, and with the small adjustments. So first thing is they use these training techniques. They use 300 epochs instead of 90 epochs used in ResNet, and they use the Adam W optimizer, and they use these kind of newest modern augmentation techniques, like mix-ups, cut mix, random augmentations, and random erasings. So, and in here you can see the in mix-ups they combine in two images with different opacities, and in cut mix they cut the image patch and insert into the different image, and random augmentation and random erasing they take some patches and remove the random number of values from the patch. So that kind of newest augmentation techniques they introduce. So, and regularization techniques also introduce newest regularization techniques like stochastic depth and label smoothing. In stochastic depth, what they did was normally during the training they skip the training process for the whole block, and in label smoothing they introduce noise to the label. So by this training improvement, they increase the accuracy from 76.1 to 78.8. Because of modern training techniques, accuracies are significantly improved. So then what they did was they changed the macro design. They insert the macro design, various macro designs. In here first they did was in here in ResNet 50 they used the block numbers something like that 3, 4, 6, 3. In the swing transformers block numbers count like that. So they improve that block numbers 3, 3, 9, 3. In different blocks works on different resolutions, so they improve the block count like that, and they change the stem cell in standard ResNet. In standard ResNet architecture, we use the stem cell for cell like 7x7 kernels followed by max pooling with both strike 2. So stem cell we used for downsampling the input resolution when at the start of the model. So in this ConvNeXt architecture, what our model, it's directly use the 4x4 kernel with the strike 4, that for the downsampling the input resolution into the
it's directly from the swing transformer.
Yeah, it's in transformer also they use that. And yeah, then they introduced the depth-wise convolution here, so that is also similar to the like self-attention in the swing transformer. So from this improvement they improve the accuracy from 78.8 to 79.5. Then they introduced ResNeXt, defining their next model. In ResNeXt paper they introduced the group convolution kind of things into the ResNet architecture. So in the group convolution it's worked like that. There are several groups for the different features. So this for the equivalent diagram for this network, and you can see with this there are 32 different groups, and after finally combining you can get the 82 128 convolution. So special type of group convolution we call the depth-wise convolution. So that each group has different kernel for each patches. From this improvement, they raised the network performance to 80.5. Then they introduced the inverted bottleneck architecture. So in inverted bottleneck architecture, block has the higher dimension compared to the input and output. This internal in the block, this internal part has the higher dimension than the input and output. So in ResNeXt paper, which the ResNet input paper, it has architecture like that, and they inverted that and get this bottleneck architecture. So because of that, the increasing the computation for the depth-wise convolution part, but it significantly reduced the computation in the input and output shortcut connection part between this. So yeah, from that inverted bottleneck insertion made the accuracy increase from 80.5 to 80.6. Then they use the various kernel sizes for the depth-wise convolution. I previously mentioned that transformers have the non-local self-adhesion mechanism. It's make the attention to the attention globally. So like that, in convolution we have the small kernel sizes. So I think they're trying to do like if we increase the convolution kernel size, it's something like close to the self-attention mechanism, because it's make the larger attention to the whole image kind of things. So but while they doing the experiments, they found that the kernel size 7 gives the better result. When we increase further, it's reduce the accuracies. So they choose the kernel size as 7 by 7 for the depth-wise convolution part. So yeah, and in here they finally did the this depth-wise convolution move up, and from that moving up part, the accuracy is reduced bit of, and after that kernel size increasing the kernel size, they got the better accuracy. So yeah. So then they went into the micro level design. So in the micro level design, what they did was they did some changes into the ConvNeXt block inside. So they simply insert the GLU activation other than the ReLU, but they mentioned that they didn't get any improvement from that. But in transformers, in original transformer paper also, I think they use the ReLU. In transformer they use GLU activation. So then in transformer we can see it has several low number of activation layers, and in the ResNet architecture we can see several activation in each end of the intermediate block layers. So by using low number of activations, they increase the performance by 0.7 and achieve the 81.3 accuracy image on the ImageNet dataset. And then they use the fewer number of normalization layers, and they substitute the patch normalization with the layer normalization. So because of that, they got the higher accuracies from that improvement. Also in here you can see that they insert the patch normalization, they insert the layer normalization rather than the patch normalization. So and then for the downsampling, after this kind of block, we have to downsample the input resolution. They use this 2x2 convolution layer with this type 2 for downsampling, which is separate layer. Because of that, they improve the accuracy to 82. So and with that they surpass the swing transformer accuracy. So yeah, these are the results they have achieved by training the swing transformer tiny model with the ConvNeXt tiny model. It's the counterpart of the swing transformer model with the same number of parameters, and we can see ConvNeXt counterpart is always performing better than the swing transformer. So this for the ImageNet 1K train model, and with this in here with the ImageNet 2K pre-train model. So these different kind of variations of the ConvNeXt models, we can see different number of blocks they use, and the intermediate block dimensions are changing each blocks. That's how they get the ConvNeXt large model, extra large models. So in here another point is they has the higher inference throughput than the swing transformers. You can see when it has the higher inference throughput, so inferencing is much more easier than the swing transformers in here. And also in ImageNet 22 pre-trained model, we can see that because of this large number of, in here we know ImageNet 22K has much more larger data set. It is more larger data set. So we know the transformer model needs much more data for the training, and even that situation also ConvNeXt models perform well with the large number of data than the swing transformer models. ConvNeXt was EID. What is the isotropic architecture means? This has the same, which don't have the downsampling layer, and in each block they use the same resolution for the feature maps. It's more close to the swing transform architecture. That's why they try the isotropic convolution architecture. So they check the ConvNeXt block structure the same without changing the feature dimension. So in here also they get the better accuracies, comparatively better accuracies. In here the object detection and segmentation kind of segmentation results, and in here also you can see that they giving the better average precision accuracies with the segmentation and object detection task. In this one for the semantic segmentation with ADE to ATK data, in here also they perform ConvNeXt model with the swing transformer. And with compare we can see that they gives better performance. So, and in the flop count also we can see the ConvNeXt model use much more bit of low flops rate. Thank you. This is the implementation I have did for the first implementation I did with the classification task with the ResNet 50 model, and it's used the 77.5 accuracy, and then I did another the training with the ConvNeXt model. Here I use backbone as the ConvNeXt model, and I did another classification task and get the much more better accuracy, 84 point accuracy with only with the 5 box on Oxford data set.
Good thing about the paper is it sort of analyzes every single aspect that can be tuned to achieve better results. Right? We can learn a lot from that. That's the thing.
One of their findings is like using convolution strike rather than coding for downsampling is good, right?
I think the stem there, right?
Yeah.
No, actually middle layers as it.
Yes, also.
Middle layers rather
They
than
use-
using cooling convolution and strike. That's the way they have used.
Can we see, look at the architecture again? Then with the you had the architecture, the architecture table, matrix table. That one. Yes. There is the okay 4x4, 90 XMR side 4. That's fine. And where do we say the stride? In the middle also they have stride.
Yeah.
Maybe not in this paper.
Yeah, it was in another table.
They mentioned that they use that method to downsample image logs, but don't use.
Have they tried out these experiments on other model except ResNet, like EditionNet or InceptionNet?
They did with the ResNet 200.
EditionNet is also there in the table. Right? 480 is the input size. To compare with the EditionNet, this one is high number of flops kind of thing, right? No. It's okay, right? 384. ConvNeXt 384 is 41.1 gigaflops. So it is, this one is better, right? Slightly less performance.
The parameter count is set, right? So one question, like, can we go to the architecture of this one? Yeah, so now they have the resonate, ConvNeXt swing and all, and we can see, like, there are 4 layers, like that's like a standard, but inside each layer they are stacking up the same block again and again, and we can see, like, in all of these models the third layer has more blocks stacked up. So what would be the reason to do that? Like,
I think swing transformer did that. I think that's it.
no, like in most of the models it's like that.
This resolution, I think, like, when we go into the deeper layers, identify more complex features and trying to identify much more complex features with that number of things, something like that.
There must be some sort of like a norm that we don't know, that neural networks are doing these things at these stages, something like that. The probability knows, but we don't know.
But I really think that it's related to the image resolution also. We are talking about 224, 384, 480, that kind of resolution. At that resolution, 14 by 14 may mean something. We don't know at high resolution what that means.
There might have been a paper that actually came up with this structure maybe. Like, initially have like small locations and then like huge number of locations and then once again do it.
We didn't even see anything. What I saw was they were very happy about the swing transformer, so they wanted to mimic the properties.
The issue was adapted from swing transform 1131.
Yeah, but in paper earlier than this swing transform also they have it. Yeah. What's the B in ConvNeXt?
Depth,
Depth
Depth.
convolution.
That's also something. When we write a paper, we start with the previous year's paper, like swing transformer, for example, and we don't go to very past years like that. Right? Those who are able to make a contribution, they get very influential papers. That's what I have seen. We are still in, look at the last year's paper, do something this year. I know.
Those papers are not from undergraduate side. Like the papers, this kind of research, these are PhD students, right? No, sir.
PhD student doesn't mean much. They have had many years to spend in the field. That you can say. But in brain wise,
Yeah.
and age wise, I think, and the professors, there's much more difference, right? They go to the conference every year and they are very much familiar compared to us. So they can quickly validate the idea students come up with. They have nothing. That advantage they have. Any other questions or comments? Conclude. Thank you very much.